All right, welcome to part 3 of our lecture series for Wednesday, May 3rd. We just got done wrapping up our pressure relationships, so let's look at now some other gas relationships that are implied based on our relationships that we saw between pressure, moles, volume, and temperature. So as we just got done talking about, we were able to combine all of our pressure relationships so that we had pressure times volume over moles times temperature is equal to a constant. So asking ourselves a question, what other relationships can be inferred based on this mathematical structure? So we're looking at relationships between variables that aren't pressure. So how about we look at volume and moles? So if I am looking at a gas that is in some kind of constant pressure system, or even then, just looking at volume and moles. Let's think about a piston. So let's say that I've got some piston here. All right, let's draw it like this. That is pressing down on some quantity of gas. And let's say that this piston were allowed to move freely. So I have some initial quantity of gas, and then I were to add more gas. We would expect that in order to accommodate this increase in collisions by the addition of new gas molecules, the volume would have to increase. So N final. So if our final moles is greater than our initial moles, we see that our volume has to expand, meaning that as we increase the number of moles, then the volume has to increase. So think about like if you were blowing up a balloon, the more air you blow into the balloon, the larger its volume is. And similarly, if we remove quantity of gas from our system, then the volume decreases. So if you were to suck air out of a balloon, the volume would decrease. And since we see same trend in one as we do in the other, an increase resulting in an increase and a decrease resulting in a decrease, this means we are again directly proportional, meaning that volume and moles has to be equal to a constant when in a quotient with one another. Okay, is this what we see from our derivation that we did earlier? So let's look. So in our relationship earlier, we have volume over moles is equal to constant. That does in fact agree with what we stated. This is not anybody's named law, but it's one that we can kind of follow rationally. And then the other one is volume and temperature. So I don't know how many of us have done this. Like, I don't know how many pyromaniacs we have in this class, but I don't know if you guys have ever taken like a sealed balloon and then you've held it over a flame, like if you've held it over like a candle before or a lighter. So we're at some initial temperature here and then some final temperature here, such that the final temperature is greater than the initial temperature. For those of us that don't know, whatever happens when you increase the temperature of our balloon is our balloon starts to expand, so much so that it expands beyond the elastic capacity of the balloon and it pops. So we see an expansion of gas upon heating it. So we would see then that the final volume has to be larger than the initial volume. So putting this in terms of how variables might change, if I were to increase the temperature of my gaseous system, then it should expand, so the volume will go up. Or if I were to decrease the temperature of my gaseous system, then the volume would go down. This is another example of a direct proportionality, meaning that the relationship between volume and temperature when divided is equal to a constant. All right, this is called Charles' law. And let's check that Charles' law is something that we see reflected. I didn't pick blue. Let's see if Charles' law is something that we see reflected in our pressure relationship equation that we got earlier. So do we see volume over temperature equal to a constant? Up here, volume over temperature equal to a constant. Yes, we do. All right. So what we're going to do now is we are going to take a closer look at this equation, because this equation is actually an equation that is known by a special name and has a few special variables and is actually quite useful when talking about gases. So up next, we are going to discuss the ideal gas law and how to apply it.